expression says. If I have a positive slope, and that slope is equal to negative delta H over R, what could you tell me about the reaction? Could you say if it's endothermic or exothermic? It is exothermic. Why?
Because if we put in a positive delta H, then you'd have negative.
Yes. The slope is negative delta H over R. The only way we can get a positive slope is if this term is positive, which means the delta H has to be negative, so we'll be taking a negative of a negative. So this, if we get a positive slope, it means it's an exothermic reaction.
So R would have to be negative?
No, R is never negative. R is 8.31 no matter what. It's thermodynamic constant, 8.31 joules per mole Kelvin.
So the delta H is negative?
The delta H would have to be negative. Yep, and that would give us a positive slope. Now, if it's an endothermic reaction, the delta H is positive. So the slope will be negative because it's negative positive delta H over R. It's great, huh? But we actually can do something with this. I want you to check this out. If it's an exothermic reaction, let's just consider this. Exothermic reaction means that as, you're not going to like this either, as temperature increases, what happens to K? To complete the sentence. As temperature increases, here's my exothermic reaction. As temperature is increasing, what's happening to K? Oh my goodness, we don't have K. We have the natural log of K. So if the natural log of K were increasing, what would be happening to K? It would also be increasing. The bigger the K, the bigger its natural log. The smaller the K, the smaller its natural log. Okay? So, yeah, it is. I'm messing with you, Katie. It's hard.
Maybe we're getting tested on this tomorrow.
Yeah, but that's okay. I mean, you got almost 24 hours.
Yeah, but I'm sleeping for like a lot of those.
Maybe not after this.
That's true.
When there's two, I believe, questions about this in the homework. They're super easy. Trust me on it. I'll show them to you. Now, this is not. This is ugly, isn't it? Okay, now, we're not done with the ugliness either. Let's think about this. I'm graphing on the x-axis 1 over the temperature. So which way is the temperature increasing? Is it increasing out that direction, or is it increasing actually this way? You know where I'm going with this. It's increasing this way. The higher the temperature, the smaller its inverse. Yes? So over here is where we have high temperature. Over here, we have low temperature on the graph. So temperature is actually increasing as we go this way. Okay, now, that's really important to see, and now you can understand the rest of it. For this graph, the exothermic reaction, if we're increasing in temperature, what's happening to the K? It's going down, isn't it? That's what I asked you to answer. As the temperature is increasing, the K value is going down. K is decreasing. Temperature, we're changing the temperature and seeing what happens to the equilibrium constant.
The itself would make it, okay, like 1 over T would, if it,
Yes, if temperature increased, 1 over T would decrease. That's why, as temperature increases, we would be going this way on the graph. It's so weird. I know. I'm asking your brain to do a lot right now. And this is only true if it's an exothermic reaction. So what I'm saying is this. Here's the point of all this. And I think you'll be able to grab onto this. If you have a reaction that's at equilibrium, it's just sitting there, right? What does equilibrium mean? It means nothing is happening. The reaction is just sitting there. There's some reactants, there's some products, they're not doing anything. That's equilibrium. If we take a reaction, if it's an exothermic reaction, and if we heat it up, what this says is that the reaction actually will shift and make more reactants. That's what I'm saying. As the temperature increases, the K value decreases. Remember what K is? It's the products over the reactants. If that ratio is going down, which is what this says, what does that mean about the reactants and products? If that ratio, I'll write it over here.
product is smaller than the
Yep. K is products over reactants. So if K is going down, what's happening in the reaction? That means this ratio is getting smaller. How can that ratio get smaller? The products have to go down, the reactants have to go up. The reaction is shifting left. That's true. That's right.
Oh, wait.
So if K is decreasing, that means this, that the reaction is shifting left. RxN for reaction. We're almost done, by the way. So you're about ready for that.
So only exothermic is when.
Yeah, this is only true for exothermic reactions.
Oh, so okay, so like let's say you have like the combustion of like okay, so like let's say you have like CO2 and O2 and then you have or no, not CO2, C2. Ugh, I can't think.
Like CH4,
Yeah,
methane, and
CH4,
O2.
O2 and it gives you CO2 and H2O.
Yeah.
So
That's an exothermic reaction.
Backwards.
Yeah, so if we heat up a combustion reaction, if it's at equilibrium, it will make more of the reactants. Yep, it'll shift to the left. Yep. Now, if it's an endothermic reaction, that means that everything is the opposite. Endothermic reaction means that delta H is positive. And so the slope of this line would be negative. Because the slope is negative delta H over R. So if you've got a positive delta H, the slope is negative. We could buy that, couldn't we? All right, I'm going to see if I can do this in a different color. Oh, you stinking thing.
Oh my god.
Oh. Ah! Not exo, it's endo. So yeah, it'll be endothermic if it has a negative slope. So for an endothermic reaction, the opposite is true. As we heat up an endothermic reaction, this K is getting bigger. For an endothermic reaction, if we heat it up, we're going to actually increase the amount of products. Now, you learned something also last year. This Kevin might remember, maybe none of the rest of you will. But that's not true. Some of you are going to pick this up. It's called the Shockley Ace Principle. You all learned it. Le Chatellier. You remember the French guy, Le Chatellier? The Shockley Ace Principle says this. If I have a reaction, X makes Y. If it's an endothermic reaction, that means heat's a reactant. Because this reaction is not going to happen unless I heat it up. That's what endothermic means. So an endothermic reaction comes to equilibrium. It just sits there, it stops. If I add more heat, what's going to happen? It's going to shift to the right because adding heat to an endothermic reaction is like adding more reactant. It shifts that way. That's what I'm also saying. Now, I wrote over there about what happens in an exothermic reaction. I'll write it here for an endothermic reaction. As temperature increases, K, look at this green endothermic. As we're going this way, increasing the temperature, K is getting bigger. Natural log of K is bigger, therefore K is bigger. K is increasing. And then the reaction shifts to the right. In the book, there are a couple of problems about this, about using this equation. It's going to give, all you have to do is plug some numbers in, and it's going to ask you about, I can't remember what the question is. Is it an exothermic or endothermic reaction, something like that. So you'll be able to answer the question. It's not terribly difficult. This is another one of those things where I want to show you what the background is, why we come out. I mean, I could just tell you this. I could tell you, well, as if you increase the temperature of an exothermic reaction, the K is going to go down. But I feel obligated to show you why that is. So even though that wasn't any fun of an exercise, you at least saw that it's justified. So if we could go a little simpler, if you don't mind going a little simpler for a moment. If K is greater than 1, knowing this is how we calculate K, what does that mean about the reaction? Would the reaction favor the products, meaning that there's more products at equilibrium, or there's more reactants? Which one is it? There's more products. Because K is the ratio of products to reactants. If K is greater than 1, that means that the numerator has to be bigger than the denominator, and therefore the reaction favors the products. So it goes without saying probably that if k is less than 1, that means that fraction is less than 1, the reaction favors the reactants. Now, what about this relationship between Q and K? I want to remind you, K is a constant. It's the equilibrium constant. K is that ratio where the reaction stops. Q can change. As Q changes throughout a reaction, it's getting closer and closer to K, normally. At the beginning of a reaction, Q is 0. And then as the reaction proceeds, Q gets greater and greater. So if Q is less than K, Q, remember, is products over reactants. So if this ratio is less than K, the ratio at equilibrium, which way is the reaction going to shift? Is it going to make more products or turn around and make more reactants? If Q is less than K, that means that this ratio is too small compared to the K, and so the reaction has to make more products to increase itself until it equals K. So it has to shift toward the products.
So why is it shifting towards Q?
Okay. Q is the ratio of products to reactants. At the beginning of a reaction, you don't have any products yet, so the numerator would be 0. You have all reactants, so it's 0 over however much reactants you have. So Q is 0 at the beginning. As soon as a reaction starts and starts going to the right, we're going to be increasing the numerator and decreasing the denominator. So Q is going to be gradually going higher. That probably is the best way to look at it. So at the beginning, if Q is 0 and it increases, then at the beginning of the reaction, Q is definitely less than K, because K is going to be some non-zero number, some non-zero ratio of products to reactants. So anytime Q is less than K, the reaction is going to continue going to the right until Q raises and equals K. If Q is greater than K, that means that the reaction winds up being product heavy, and it's got to shift back left until it equals K. When Q equals K, that's when the reaction stops. That's equilibrium, when Q equals K. So if Q is less than K, the reaction is going to make more products and increase until it becomes K. And if Q is greater than K, it's going to shift and make more reactants. Okay, and then down here, it's just going to remind us that anytime you have a delta G value of 0, that means that there is no spontaneity one way or the other. The reaction is already at equilibrium.
Please pause this interruption for an end-of-day announcement. Tomorrow, Tuesday, is the absolute last day to sign up for dodgeball. This is an event in December, the proceeds of which will go to mental health awareness. If you cannot sign up tomorrow or you have questions, please see Mrs. Clark in room 201.
So yeah, that idea of Q, and we can all see, okay, fine, Q is the products over reactants, but if K is the products over reactants too, how are those two related? Just remember, the Q can vary. As the reaction proceeds to the right, Q is steadily increasing because the reaction is making more products and using up its reactants. So Q is going up. As soon as Q is equal to that ratio in K, then the reaction stops at equilibrium. And at equilibrium, Q is equal to K. So until you get to equilibrium, the reaction is shifting right, and Q is less than K. And if somehow you get a situation where Q is greater than K, it means the reaction has gone past equilibrium. It's going to shift back to the left until it equals K. All right, my friends. Now, there's not anything that we didn't talk about or I don't feel like you have a good handle from today on. Don't get too worked up about it. I won't put it on the quiz. You can bet that delta H minus T delta S is going to be on the quiz and things like that. But what we went into today, you're going to find as you go through the rest of the problems that you didn't really miss anything.